Swayam Prabha. Digital India. Educated India.
Okay, good morning guys. I'm Siddharth. I work here at the Department of Physics. Okay, and the aim of this lecture is to convey the strangeness of this field. Okay, the field is called quantum mechanics, quantum physics, whatever you want to call it, and the idea is that it's quite strange. Okay? However, although it's strange, it seems like we can make use of it without even really understanding it. That's even stranger, right? So that's the idea. So it's a journey of more than 100 years. Obviously, I won't be able to convey everything. So it's going to be fairly superficial. At the end, the message is that it's quite strange. If you want to learn more, please learn more. Okay? This is just the beginning. Okay? So let me start with that. By the way, this is Schrodinger. Quite confused about the cat, which might be dead or alive or both or none. Okay, that's the idea. Okay, so let me start at the end of 19th century. Okay, anyone knows this guy? This is Lord Kelvin. Okay, you know Kelvin. I think you have learned about Kelvin, right? So Lord Kelvin, he was president of the Royal Society in 19th century. You know where Royal Society was? In London, right? So he made amazing contributions to the theory of thermodynamics, right? So at the end of 19th century, he said something like this. Now, this might be wrong and people might be blaming him for no reason, but people, oh yeah, please come in. The idea was, that we have actually made huge progress in the field of physics, right? We now understand thermodynamics allows us to make fantastic steam engines, big industry, right? So we do something in our office, solve some equations, and it seemed to actually work in reality, right? So we have explained lots of things. I'm talking about what has happened in up to 19th century. We can talk about celestial bodies, right? Newton's laws. We can describe them. We understand. There are a few things here and there that we don't understand. Maybe Mercury, why it's moving like that. Maybe there is some additional planet there. We don't know, but maybe it's a minor thing, right? Then came Maxwell, Faraday, right? They did all these experiments related to electrodynamics, right? Now we understand how the electromagnetic wave actually moves. It does not require any medium, right? The charges, how you can get electric and magnetic fields, how they are related. All of that had happened by the end of 19th century, and that's why Lord Kelvin or someone like him, okay, because in this era of misinformation, you can't really know if this is his quote. But anyway, I needed to show someone, so I'm going to show his face. Okay, so what did he say? He said, there is nothing new to be discovered in physics now. Okay, we're talking about more than 100 years ago. All that remains is more and more precise measurement. Okay, however, the universe didn't seem to agree. And then I'm going to talk about a couple of experiments that gave rise to a revolution that happened in the earlier part of 20th century, which we call quantum mechanics. Other things also happened. Relativity, I'm not going to talk about it, okay? Even quantum mechanics, I'm not really going to talk about it. I'm just going to give you like a dramatic version of what happened, okay? Okay. So now, what happened really? So the birth of quantum physics, why did we need to actually change this paradigm? Okay, we were living in this very nice classical world of billiard balls hitting on each other. If you know the initial state, you can get the final state, right? Which equation allows you to do that? F equal to ma, right? You know the force, you know initial position, you can calculate final position. Very simple. Now things can get complicated, the forces can be complicated, they are all vectors, so you have to add them, x component, y component, things can get very messy. But that doesn't mean that it's not possible. Maybe you need a gigantic computer to do that, but it's not impossible in principle, right? That's what classical mechanics had told us, completely deterministic picture. But then a few experiments started to happen. Now a simple experiment, right? You take this tube light, right? You know what's actually illuminating inside in this tube light? Are you sure about it? No? Anyone else? These tube lights actually look slightly different than before, right? You agree? LED, okay? LED. I'm not going to go into LED, okay? I've worked on LEDs, but I'm not going to talk about it. But what you can actually do is, you can take a prism, okay? And take this light from this particular tube light. It will go through the prism and it will break into its components, right? So this might seem white to you, right? So you might expect that it's going to be a very continuous spectrum. It's not like that. So this is actually made out of 3 LEDs, blue, green and red, okay? But for our eyes, it looks white because we have only 3 perceptors, okay, in our eye. So you combine all of these, you get a white light, okay? But the point is that you use a prism, you use some kind of a monochromator or something like that, it will break down the light into its original component, right? So what people did at the end of 19th century is that they started with this hydrogen gas, they applied a huge electric field. It ionized the gas, the gas started emitting light, okay? And the strange thing was that if you take that light and go through the prism, what was happening? You were getting like extremely discrete lines. It was not continuous, and none of the dynamics in classical physics, Newton, Maxwell, none of it discretizes anything, meaning everything is continuous. I can push this thing with whatever force I like. It can be extremely tiny, it can be extremely large. There are no boundaries, there are no thresholds in classical mechanics. So for the first time, we started seeing these extremely discrete energies. Okay, first observation. Okay, something to do with discretization. Okay, something that did not exist before. Second thing, black body radiation. What does that mean? Any object which is at a particular temperature will emit radiation. Okay, you all have seen some red hot iron, right? Why does it look red? Why sun looks the way it looks? Because every hot object is trying to thermalize with the environment, right? So it has higher temperature than the environment, so it will give off its heat, wants to come to the thermal equilibrium state, right? So now, if you look at the spectrum, okay, you can look at sun and then record the spectrum again. And you will get a very peculiar spectrum. And that spectrum is associated with its temperature. If you actually move your spectrometer towards some blue star, it will have a different curve. What does that mean? It means that it's actually much hotter. Okay, so somehow temperature, if you actually have an infrared camera, you point at me, you will see that I am also glowing, right? My temperature is not as crazy as sun, but I'm still glowing, okay? So everyone does that. So what does it mean? It means that somehow the temperature is associated with the radiation, and no one was able to actually, we could do these experiments for different objects at different temperature, but no one could actually explain why this is happening, why energy is somehow related to wavelength and all of this craziness. No one could explain this. One more interesting thing is that in early 20th century, everyone knows about Rutherford's experiment, maybe, right? So he came up with this model of electron orbiting around nucleus and blah, 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 right? But we had learned in the 19th century that if you have a charge that is moving in accelerated motion, is going to radiate actually, like what you see here. There is a charge, you move it, it will actually send off the radiation. If it sends off the radiation, it means it's going to lose its energy. What happens if you lose energy? You are going to go to the ground state. So eventually the electron should actually end up in nucleus, because electron is a charged particle, right? That means that our universe should vanish in a blink of a second. Okay? We are here. Why are we here then? Right? So it's like a so fundamental question that we could not answer. Okay, a couple of more examples. Photoelectric effect. The experiments were done earlier, but then Einstein explained this effect. So in 2005, he came up with 3 groundbreaking papers at the age of, I think, 1905. Came up with groundbreaking papers, spatial theory of relativity, Brownian motion, which actually proved that atoms exist, and photoelectric effect that proved that the wavelength is related to the energy of a photon. Okay, a photon is a particle and the energy depends on its wavelength. How do we know that? So you start with a metal, you shine some light. Okay, let's say I've got this red laser, right? I shine that red laser, I make it very intense. Nothing happens. Suddenly, I change from red to blue and I start getting electrons. Okay, so what does this tell you? That intensity doesn't matter. What matters is wavelength. So if wavelength should be related to the energy, intensity is just how many particles you have of that energy. Okay, unless you have enough energy, you are not going to knock out an electron, even if you put lots of photons. That's what it shows. So in a way, all of these experiments, what are they showing? That a photon, which supposedly is a wave, right? It's a light wave, electromagnetic wave, which is what Maxwell did, right? We see that it's a particle. That's very strange. Is it a wave or a particle? No one knows, right? Then we have these discretization, and this is fantastic, right? This is actually from the diary of Becquerel, right? Henry Becquerel. Have you heard that name? 1896, I think. He was an experimentalist. What did he do? He had some uranium. No one knew about radioactivity, right? He had some radioactive material in a flask and he had some photographic plates, right? So how do they work? Actually, photographic plates, you actually, if you have some radiation around, it's going to turn them into black or whatever, expose them. Olden days camera, you might not have seen it, right? Too young to see this, but anyway. So what he did is that he was doing some experiments. He had some photographic plates lying around and coincidentally he put the flask filled with some radioactive material on top of the photographic plate. He left, came on the other day, saw that the photographic plate was exposed. He had no light in the lab. It was a dark room. Where did it come from? Right? So then he thought about it, and what you see here is a real video. Okay? What is this? This is a cloud chamber. What is a cloud chamber? You fill a particular tube with low temperature gas or a vapor. Okay? And then you put, let's say, some uranium or some radioactive material inside. Now this radioactive material is actually shooting high energy particles. What do? They actually ionize this vapor as they move. What do I mean by ionize? They rip the electrons from the vapor, right? And then they're creating these tracks. Okay? So, you know, Marie Curie actually led this research. She got 2 Nobel Prizes for discovering these things. 2 Nobel Prizes, right? She died because of radioactivity, if you don't know, okay? Because she did not know that it also causes cancer. If you go to her office, the doorknob still radiates. Okay, it has got higher radiation than usual. Okay, so she was covered with radiation in a way. And but anyway, the point is that all of these fantastic things were happening. Now, in order to have energetic particles inside nucleus, you cannot have them like balls. You cannot put them inside. So they must be in like wave-like form, and then waves are shooting out. I mean, this was all very strange. Okay, this happened from, let's say, 1995 to 2005, 10 years, and then we had this statement by Lord Kelvin saying, oh, it's almost done, and within 10 years we have so many experiments and we can't explain any of them. Okay, so that was the scenario. So what all of these experiments actually show is that energy and wavelength seems to be related. Okay, particles can also behave like waves sometimes or something like that. So let me illustrate. So I can't go over all of these experiments, but what I'm going to do is I'm going to focus on this double slit experiment. Has anyone heard about this double slit experiment? Yes. Okay. So in a way, it's not an experiment that was done for quantum physics. I think Thomas Young in the 1800s did this experiment to prove that Newton was wrong. So Newton has this had this corpuscular theory of light, right? Particles. Light is a particle. That's what Newton said. He did some experiments and showed that it's a particle. Then this Thomas Young wanted to show that no, it's a wave. How do you show that? What you do is actually you create these two slits. You shine a wavelength of a particular wavelength of light. It goes through. What will happen if you have a wave that goes through two slits? Or let's forget about that. Have you learned about what happens if two waves come together? You get some interference, right? Constructive, destructive, blah blah blah, right? So if you have a wave, then interference is obvious. Amplitudes get added, they get subtracted depending on the phase, and blah blah blah, right? So if you have a wave, it happens with water wave, sound wave, whatever, right? If you have a wave, this is bound to happen. So he devised this experiment back in 1800s, showed that light is a wave. Then Einstein in 1905 again said, no, it's not a wave. Guys, it's a particle. Okay? So they kept fighting for 400 years. Wave, particle, okay? And we still are fighting in a way, okay? I'll talk about that. Okay, so what is the experiment? We are going to do this experiment, okay? Now, this comes from I need to cite, okay? I need to refer you to, I watch lots of YouTube channels, okay? I've been following lots of channels for last 10-15 years, okay? So I would recommend, whenever you have some free time, I know you are quite busy these days, but whenever you have some free time, so this domain of science is a very nice channel. You can go over the animations, beautiful animations. And the other one is Veritasium, is something that I recommend. I have also got some slides from that. So at least some inspiration, right? So what is the experiment? I have got this paintball gun. You know what a paintball gun is? Maybe, maybe not. I mean, it's a gun which has got paint balls. Okay, it's paintball. So what's the experiment? I have the gun. I have a wall in front of me with two slits, and there is another wall beyond the wall. Okay, and I have this paintball gun. Now the thing is, every time I push the trigger, I get some recoil, right? So what's going to happen is that every time I shoot, I'm not going to shoot exactly at the right position. So it will actually go all over the place, right? And then I'm looking at the screen. This is my screen, okay? This is what will you see? I mean, there is nothing strange happening here, right? This is what we expect. What do you see? You get some paintballs here, some paintballs here. Why? Because they have gone through this slit, right? These ones have gone through that slit. Have you learned about probability? Yes. Right? So you can actually draw a probability distribution of this, right? You will see that you will get a maxima, some kind of a bell-shaped curve you will get, right? Okay. So how do you actually explain that? This is simple. If you have only one slit, Okay, if you have only one slit, you get this distribution, bell-shaped curve. Why bell-shaped? Because in the middle you will get maximum population of paintballs, and then it will decay because at the edges there will be some deflection and all, but let's not talk about that. Okay, and then you will have P2 if you keep this slit open. And what's the total probability distribution? P1 plus P2. Very simple, no issues with this, right? This is what happens with ordinary particles. Okay, now let me do this experiment with electrons. Okay, so you can get electron gun actually, which spits out one electron at a time. Okay, so we are going to do this experiment. Again, obviously, I'll have to shrink all the dimensions. Okay, it's not a wall anymore. It's like a small slit made in the metal, blah blah blah. But overall, it's the same. Okay. Okay. So now we have this electron gun. We are shooting it. Initially, it looks very similar to our paintballs. Looks okay. We get blip, blip, blip. What is this detector? This detector actually has lots of pixels. Every time an electron hits, it gives off a light or whatever, some current, something that you can measure at each pixel, like your camera, right? So this is like a camera, and every time an electron hits, it gives you a blip. Okay, that's my screen. So initially it looks very similar, but then what happens? You keep doing this experiment, something interesting starts to happen. You get this interference pattern. Okay. Then you say, okay, maybe electrons are indeed wave. Okay, they're not electrons like balls, solid objects. Maybe they're distributed. They're not like zero dimensional point objects. They have some distribution. Okay. Why do you say that? Because we know that we can get interference. We can easily generate that pattern. If you consider this electron to be a wave. Okay. How? Because you have a wave source. It goes through, and then you get two sources, point sources. They will interfere, and then you will generate actually. So you can, what's going to happen is that you will get, if you close one of the slits, then you will get this intensity profile. If you close another, you will get this intensity profile. But when you have both of them open, you get this interference pattern. Now this is intensity. Intensity is actually square of the electric field. If we are talking about an electromagnetic wave, intensity and the field, electric fields are different. So in the actual wave, electric field is oscillating. What you see is the intensity, which is square of the electric field. Okay. But then when you actually add, you add electric field. You don't add intensities when you're doing actual interference experiment, right? At each point, electric field is getting added or subtracted. And the eventual outcome is that the intensity shows these bands. Okay. So what do we need to say as far as our electron is concerned? We are going to say that electron is actually like a wave. Okay. So let's do that. Let's free our mind and say that the electron is actually not a particle, it's a wave. Okay. So it's a traveling wave. It hits this. Now, it's a crazy assumption. Okay. What are we saying? We are saying that electron is everywhere at once. Okay. So it's you might think it's a minor modification, but it's not. Okay. So, okay. Then obviously with this modification, you can see that another question arises. It's a wave of what? In case of electromagnetic wave, it's electric and magnetic field oscillating. Wave of what? What is oscillating here? How? Why? Electric field of an electron should not oscillate, right? It's a charged part. Sorry? Electron field. Have you taken a course in quantum field theory or what? Okay, good. So yes, so some kind of field that is oscillating. We don't know what is. We are just trying to explain the results, right? Okay, so something's oscillating. Okay, we are going to call it psi. Okay, whenever we want to look smart, we use Greek letters. We don't understand it, but we look smart, right? So psi. So psi is equal to psi 1 plus psi 2. Interference will happen. Okay, what does our wave theory tells us? That if you now put a screen, the intensity should be psi square. Fantastic, we have solved the problem, right? But what is happening? Overall, we do get the interference pattern. But for every electron, do we see the pattern? We see one electron at a time. You understand the difference? If you do the experiment with water waves, you will see the whole interference pattern, right? But with an electron, what is happening? If you do the experiment millions of times, then you will get the pattern. But for each and every electron, you just get blip, blip, that's it. So is it a wave or a particle? It's neither. Okay? So then both. Okay, neither, both. We have got all possibilities, right? So with that, we have these two problems, right? One problem is that with this scenario, we don't know which slit it went through. If it's a particle, then it should go. Like I can come through the door, not through the wall, right? So it has to choose the slit if it's a particle. If it's a wave, then we should see the pattern. Okay? So that's the conundrum. So this is the real video. If you do the video, this is what's going to happen. Okay? If you do the experiment, this is what happens. Eventually, you will get the pattern. Okay? So let's say, okay, let's try to actually make it more clearer. What I'm going to do is I'm going to put two detectors in front of the slits. Okay? So then you can say, then I'll know which slit it went through. Now I'm tracking all the time the electron. It can't escape. So I'm going to put these detectors. If I put those detectors, I'll know which slit it went through. What happens in that case? Interference is gone. Oh my God! It's like, it feels like a very big conspiracy, right? Feels like that the universe does not want me to know. Yes.
What are those detectors?
These are, I mean, you can have different detectors. The electron, these are mostly semiconductor detectors. So depending on, back then people were using something different, but these days you can really detect single electrons. So what happens is, if electron hits, it will actually, it can have different mechanisms, meaning it can generate some light either, or it can accelerate and knock out even more electrons. It can create this avalanche and give you a current. So depending on what material you are using, you can actually have different detectors. Mostly these days made out of semiconductors, meaning silicon or something like that. Depending. So this is actually kind of what the detectors that CERN uses, LHC, Large Hadron Collider, right? It's detecting these particles. For each of different particle, you will have a different kind of detector. Now, in this particular case, electron has some mass and some charge. Based on that, you design your detector, right? If you are trying to detect a neutrino, then you need a different detector because it's neutral, right? I mean, all sorts of things, and the mass is extremely, extremely tiny, right? So it took a lot of time to actually detect neutrinos. Okay, let's just recap. Okay, so what do we have with waves? We have got interference, no issues with that. Let's say we have electromagnetic wave, the electric field gets added, the intensity is a superposition. We call it a superposition principle. Okay? With particles, no interference, the final distribution looks like that. Okay? Quantum, what do you have? You have this, similar to waves, but then when it hits the screen, you get one at a time. Okay, so kind of a mixture of both of these. Okay, so whenever so what happened is, people were trying to explain all of this, right? And in the process, it took around 15 years. Started with Einstein, then started with actually with Planck, I would say. Planck did not even believe his own paper. Okay, Planck wrote something to explain black body radiation. Okay, he was smart. What did he do? He had a curve. You guys do it. I know in some of the exams, if you know the final answer, you backtrack. Okay, that's what exactly Planck did. What he looked at the curve, he said, oh, if I want to generate this curve, what formula should I use? Okay, that's what he did. He added that term in the formula, and then he said, oh, but I can't believe this formula. This formula is telling me that E is equal to some constant multiplied by frequency. Okay, and then that doesn't seem right. But then he did not believe it, but Einstein believed it. So he used that formula to explain photoelectric effect. And then de Broglie took it even further. He said, oh, it's not only photons that act as waves sometimes. Everything does that. You, me, everyone. Yes?
What constitutes measurement in the quantum sense?
Yeah, that's the whole point of the cat. That's the whole point of the cat. Okay? So Schrodinger, this is another Schrodinger. Okay? Happy Schrodinger. So if you give a correct prompt to ChatGPT, that's what it generates. Okay? Happy Schrodinger. Okay? So this is a photograph from Solvay conference, I think 1927 or something like that. It's, by the way, 100th anniversary of quantum. It's the year of quantum. Okay? So around in 20s, people were formulating quantum theory, but 1925-26 is when Schrodinger came up with this Schrodinger's equation. Okay? Now, that's why I don't want to give him credit only, because there were so many people involved. By the way, only one lady scientist in the whole thing. Okay? Okay? I see it flipped, which is good. Okay? Anyway, what I'm trying to say is that all of these people contributed, and then they came up with this equation. What does this equation tell you? Okay, so it's like a F equal to ma like equation. You start with some wave function psi of a particle, okay, some wave associated with electron, initial state. This equation will tell you how it's going to evolve as a function of time. So it looks very similar to every other equation. It's a differential equation, which is what we use in physics, right? F equal to ma is also a differential equation, right? You agree? Acceleration, you know all of that, okay? So it's a differential equation. If you know the initial state, you get the final state. That's good. You can explain lots of things with that, right? This is actual simulation of a double slit experiment. Okay, so you make this electron very, I mean, by big, I mean the scale is tiny there, okay? We're talking about angstroms or less than angstroms, okay? But then you can explain all of these things. What you are saying is you start with this wave function, okay? And then it will evolve as a function of time. It will generate this. But the crazy thing is that now you are saying, I know the final state in terms of probabilities. Where are probabilities coming into play? Because what you are doing is you are calculating the wave function, right? You are calculating the wave function. But whenever we make a measurement, it seems like we can't see the wave function. We see psi square, right? So in principle, they also made a huge leap saying that this psi actually can be complex. You know complex numbers? Okay. Which seems odd, but then because you can't really see it, psi square is always going to be real, right? So psi is complex, psi square is real, but because it's complex, It looks complicated. It does something very complex, okay? Because you can add size, all real and imaginary parts. You can have all of these interference, which is what you're actually seeing here. This is like a particle in a box. Okay, it can do all of these things. You can calculate, you don't need to use time dependent equation. If you use time independent equation, then this equation tells you the orbits of electrons in hydrogen atom. You know these p orbitals, s orbitals, right? The shape. How do you get the shape? You solve this equation. That will give you the shape of the wave function. So whatever shape you are seeing actually is not shape of an actual orbit of an electron, right? People show this dumbbell shape, right? It's not like electron is actually doing that. It's the cloud, it's the psi that we are plotting. Okay, if you plot psi, it's a cloud, a probability cloud. If you make the measurement, then you will find electron somewhere there with some probability given by psi. That's what it means. So it could explain lots of phenomena, but not the obvious world around us. Because I see you at one in a chair, right? You're not distributed. This person is not like moving around, delocalized. You're quite localized. So how do I explain this? Meaning this is all good, right? So then Bohr came up with the idea, you see, we don't need to worry about it. This only happens with these tiny particles, subatomic particles. We live in the classical world. We don't need to worry about it. But that's strange. We are made out of atoms. So we should be able to explain this, how the classical world actually arises from quantum. That should be obvious, right? Okay, so he devised, to actually make his point clear, he devised an experiment. Okay, the only thing that I can say at this point is that he definitely used to hate cats. Definitely used to hate cats. Okay, I think his daughter also said something like that. But anyway, okay, so what's the experiment? It's quite devious, right? We have a box, we have a cat inside. Okay, there is this hammer, there is this cyanide flask. Okay, and there is this radioactive atom. By the way, this was taken from Veritasium. Okay, all credit goes to him. Fabulous channel. Okay, so let's start with our initial wave function of this system. Okay, so what is Schrodinger trying to say here? We are made out of atoms. So let's just extend the idea of quantum mechanics to macroscopic world and see what happens. What it is telling us. Okay, state 1, no radioactive decay and the cat is alive. That our initial state. We made sure that that's the state. We started that. Okay. So now, as the system evolves, no one's looking at it, system is evolving. What happens is the way you, if you use our Schrodinger equation on this state, what will happen as a function of time is that it will evolve into a state which says that the radioactive atom has decayed and not decayed simultaneously. Like our electron, right? It has gone through slit 1 and slit 2 simultaneously. If you just let the electron travel, even if you start here, that doesn't mean that it's going to stay there, it will evolve. Okay, and Schrodinger's equation is going to predict that. So that's what happens. It will evolve into a state where it has decayed and not decayed. Now, if it has decayed, then the mechanism is arranged in such a way that the hammer actually will break the flask. The cyanide will come out of the flask and the cat will be dead. Okay, so now we are in a state. What is the state? The state is this has decayed and not, the hammer has fallen and not, the flask is broken and not, the cyanide is out and not, the cat is dead and not. Okay? This is quite crazy, right? But you can actually show that if you do, not for the cat, but these days people call cat states. Okay, I'm going to get there. I hope I can get there. Okay? So now, so we have got two states in a way, two states possible, that the decay has happened and the cat is dead. First state is decay has not happened and the cat is alive, but in between it's evolving, it's in both the states simultaneously. Okay? I mean, mathematically speaking, I would write it like this, but that's fine. Okay? So now I come, okay? It's in this state, okay? It has decayed, cyanide is out, the cat is dead, not decayed, cyanide is intact, the cat is alive, right? Now I come, I open the box, I see only one of the outcomes, either the cat is dead or the cat is alive. I never see it in this superposition state, so-called superposition state, right? So what does it mean? Just think about it, right? Quite a strange experiment. Schrodinger is doubting his own equation, what the equation is telling, right? So you can actually use that equation very deterministically to evolve a state like what we saw, like F equal to ma, right? You can use it. If you know the initial state, you can get to final state, but when you actually make the measurement, you get only one of the outcomes. You don't get actually the whole superposition state. Okay, so what does it mean? It's showing you that if you try to apply quantum mechanics to the real world, something absurd is happening. Something absurd is happening. We can't really explain how this classical world directly emerges out of this quantum world. That's number one. The second one is this: what actually constitutes a measurement, like what you said? What is the measurement? Do you need a person to do the measurement? If another cat comes and opens the box, what will happen? Do you need a photon? What about photon? No cats, no boxes, no human beings, just a photon. What will happen? Same thing? Okay, so it seems like you know the answer to the measurement problem. You should write a paper. No, I'm just joking. What I'm trying to say is that it's still not clear basically what constitutes a measurement. Okay. Now things have improved in last 100 years. There is a theory of decoherence, quantum Darwinism, pointer states. Lots of things have happened. I'm not going to go into those, but this is the point that he was trying to make, that we don't understand exactly how this classical world emerges. What is the role of the observer? For the first time in physics, we are talking about observer. We are not only talking about the phenomena, right? We are saying that the observer actually is changing something. It plays an important role. It makes, the observer is making the measurement and deciding the final outcome, whether the cat is dead or alive. There are lots of theories like multiverse. Maybe both the things happen. The universe just breaks. Blah, blah, blah. I don't want to go into speculative theories at the moment. The point I want to make is that Schrodinger himself came up with all of these things which showed the strangeness of the theory that he and other people put together, right? So obviously, yes, what was your question?
So the double-slit experiment,
yes.
the electrons or whatever particles, they interact with the slits themselves, right?
Right.
Why doesn't that count as a measurement or observation?
Yes, good question. You do the math, you will know. Basically, it has to do with decoherence, what causes decoherence and what doesn't. What is a decoherence? It's a loss of quantum information. So whenever system interacts with its environment, what is happening is we cannot actually, so if the photon actually bounces, it is going to actually get entangled or interact with me. It will take some information in a way, and if you cannot keep track of it, then you have lost that information. And that's what counts as decoherence, and that in a way allows you to explain why superpositions are not observable, in a way, not entirely, but in a way. So, okay. So obviously you would think the theory is so non-intuitive, obviously it has no application. Only physicists are fighting about this theory. There is no application of this, right? What's the point of this? It's fun, it's interesting, but it seems quite harmless, right? That's not the case. We are using it. We are using it very effectively, right? So this is a very nice cartoon series from Caltech. You can go and check this out. So the answer is that no, we are actually using it without actually understanding how exactly it works. Maybe that's what I say. Many people believe that you don't. This question is all nonsense. We should not talk about this question and all. But anyway, and I'm going to give you 3 examples. Okay, there are lots of examples. I'm going to give you 3 examples. So you know how the microscope works, right? Optical microscope. You have some light. It goes through some optical elements and you can image something, right? Can you image something that is smaller than the wavelength of light? Can you actually take a look at, let's say, atom using an optical microscope? No, you can't, because it's like using a big ruler to actually sense a small ball bearing, right? You will keep hitting it, okay? Okay, so wavelength needs to be actually smaller than the object that you are trying to image or measure. Okay. So now if you want to measure something that is really tiny, what other waves do you have? You're saying the equation says that electron is actually a wave. Can we use that? We can indeed use it, right? We can use an electron microscope, right? This is a real image of an ant's head. You can actually see each and every hair, and that hair is in nanometers, hundreds of nanometers, yes, microns. Few microns are hundreds of nanometers. Even more impressive, this is a transmission electron microscope image of a crystal, and you can see a missing sulfur atom. A missing sulfur atom is what you can see. Okay, so we are using it very effectively. This electron wave, whatever it is. So these are all examples related to quantum, the double slit experiment, right? So what did we see? You put a detector here, what will happen? It detects and the final outcome changes. Can we make use of it? Maybe yes, we can. This is known as quantum cryptography. What happens is that there is a spy who's trying to listen to my conversation with the other party. Okay, I'm trying to send some information, and there is some spy. I'm one of the most important persons in the world. Okay, I'm trying to send some information, and then some spy is trying to decode it. If you are sending some classical information, I would not even know. If I'm sending quantum information, what will happen? The act of actually knowing the information will change the information. So I'll know. We can make use of it. Where people are trying to actually make use of this. People call it quantum cryptography, quantum communication. Okay, something of that sort. So this is indeed very useful.
What is quantum key distribution?
Okay, I won't be able to explain the whole thing, but this is in a way.
Same thing.
Yes, related to this. Yes, it's how you can actually securely send this quantum information. Okay, so it's one of the protocols. Okay, okay, and then the final example. What did we see? That until the time you measure, electron is like a wave. It's everywhere. It interferes with other waves, right? Can we make use of it? Maybe we can. How? It's traveling through both the slits simultaneously. It's the ultimate parallelization. It's exploring multiple paths simultaneously. Not only that, it actually, if something else is exploring multiple paths, it will interfere it with the other entity. It will do something very complex. So in a way, you can explore whole bunch of paths simultaneously. Ultimate parallelization. Where is it useful? In computing, right? So people are trying to use it for computing, quantum computing. That's what it is. Okay. So obviously I have not talked about entanglement. Okay. That's another or the most important key as far as this is concerned. But okay, someday, some another day we'll discuss about this. So, what's the crux at the end? We are yet to unravel the mystery of the cat. Okay, at least for me. We don't understand it exactly, at least not intuitively. However, the cat doesn't seem to mind too much, right? We can still make it useful. Okay, people are actually using cat states for doing quantum computing. They call it cat states, not real cat, by the way, not real cat, but they have got highly delocalized ions or molecules, something of that sort. What do I mean by delocalized? It's not in a particular position, okay? It's very distributed. So they call it cat state, okay? These are fairly big. It's not an electron. It's fairly big. It's like molecules, ions, big particles, okay? So that's where I want to end. Okay, if you have any other questions, I'll be happy to discuss those. Thank you. Yes.
So is it that we can't observe the superposed states because they exist in some other dimension?
Not really. I mean, we can still work in our usual 3 dimensions and show that due to this decoherence, whatever I discussed, meaning because when we are looking at the cat, it's not the cat only, it's not isolated from the environment, right? You have got air molecules bumping into it and all sorts of things are happening and we cannot keep track of it, right? Because it's just too much of information. If you start keeping track of it, you can in principle, right? But not in reality. And that's why what is happening because of that is that you're losing certain information and you can really do the math to show that you should not get superposition state for macroscopic objects, okay? Under certain assumptions. So, but that still doesn't solve the problem because what you get is what we call a mixed state, okay? Which is still going from a mixed state to a single outcome is still a difficulty. You won't get a superposition state like what we are saying, but you will get something known as mixed state. I don't have time or mathematical ability at the moment to actually drive you into this discussion, but that's what it is. You don't need additional stuff, at least at the moment. Anything else? If you are confused, the point of the talk is to make you confused, okay? That's the whole point. Because confusion is good. When you are confused, you will try to find the answers. You need to ask questions, okay? Yes.
So, like, in the recent times, we've been talking a lot about quantum computers.
Right.
This is something that is very different from whatever we've had
Right.
now. You have like qubits where you have the 0 and 1 at the same time. So
Right.
what might be the future implications happening?
Yeah, so as I said, for certain problems, because unlike our classical computer, it's not in a way hardware agnostic. So quantum software is also limited, meaning you can only run a particular algorithm, you can only solve particular kinds of problems where you get the advantage as compared to classical computers, right? So what are these problems? Mostly optimization related problems, okay? There are these problems which can also lead to decryption related thing, like encryption related things. So yes, if we manage to really have a quantum computer with lots of qubits, then we will be able to solve some what are optimization problems? Optimization problems are the problems which have lots of possibilities and you are trying to find the best possibility. Sorry? Kind of. So many problems where you have lots of possibilities and you're trying to find the best one. Okay. So some of these problems can be effectively solved using this. And many of the problems can actually be converted in problems such as these. Okay. So in principle, yes, we are I don't think we have reached that limit. I mean, there is a fair amount of hype, so you need to be able to understand what is real, what is non-real. So you should actually keep learning about these things. Yes.
So this might be a dumb question, sir.
Nothing's done.
Why
Yes.
is it that the universe has to go with randomness? Why do we need quantum? Like, why can't it be a uniform, predictable thing?
Oh, you should ask that to the universe. Meaning, the way it works is, as I said, at the end of 19th century, it seemed quite simple, right? I mean, they used to call it clockwork universe, right? You could explain all of it in terms of all of these things. But it works like this. I mean, the way physics works, maybe this is the difference between physics and math, right? You do some experiments, you get some results, and at the end of the day, you write down equations that should satisfy what you see in the experiment. This is what experiment tells us, in a way. That's what I can say at the moment. If you ask me, is this the only way to make our universe stable and long lasting? I don't know. Maybe yes, maybe no. Are there any other possible ways? Maybe yes, maybe no. People are actually working on it. That's it. Anything else? Thank you. Enjoy.
Swayam Prabha. Digital India. Educated India.